Welcome to the physics course. This topic is on uncertainty, scientific notation, and significant figures. Now we'll be talking about the scientific notation. All real numbers, no matter how small they are or big, that is in magnitude, can be written in this form: a times 10 to the b. A is a number. It can be an integer or a decimal between 1 and 10. It can also be positive or negative. And b is an exponent, which is a positive or negative integer. When we write a number in the standard form of scientific notations, there has to be one digit and only one digit to the left of the decimal point in the number a. This is the a number on the left side multiplied by 10 to the b. So a can be just one digit and it can be any number from 0 to 9. So this is an example of the standard notation. 1 is the digit that is on the left side of the decimal point, and you can have multiple numbers on the right side of the decimal point multiplied by 10 raised to a certain power. For example, 1.23 times 10 to the 6, it's like 1,230,000. This is the same number as 123 times 10 to the 4, but this is a non-standard notation. And this is in standard notation. Now let's take another number, for example, 36,600. This number is greater than 1. Therefore, the exponent is going to be a positive number. To find out what the exponent is, you can think of it this way: 36,600 multiplied by 10 to the 0, this is equal to 1. Now, to get the decimal point in its correct location for the standard notation, there can be only one digit on the left side. So we'll have 3 followed by 6600. So if we move to get that, we have to move the decimal point 4 positions to the left. This 4 position movement gives you the exponent that will be the power of 10. So 36,600 times 10 to the 0 is the same as 3.66 times 10 to the 4. Now let's take a number like 0.00563. To get this to the standard notation, we need to move the decimal point 3 positions to the right. Therefore, the exponent of 10 will be a negative number, and when we move it 3 positions to the right, this 0 will become a negative 3. So it will become 0.00563 is the same as 5.63 times 10 to the negative 3. When we are multiplying numbers with written in exponential notation, you can multiply the numbers separately and the exponents can be added. So, for example, you've got 1.25 times 10 to the 5, 1.25 times 10 to the 5 multiplied by 4 times 10 to the negative 2. So you can multiply the 1.25 with the 4 to get this, and 10 to the 5 multiplied by 10 to the 2 is the same as 10 to the 5 plus the negative 2 in the exponent area. So 5 plus minus 2 is 3. So this 1.25 times 4 becomes a 5, and the exponent for 10 is 10 to the 3. If necessary, you can adjust the exponent to leave just one digit to the decimal point. For example, if we were multiplying, for example, instead of 1.25, we were multiplying 12.5 times 4, we would end up with a 50 here. So you would have 50 times 10 to the 3. So you could convert that to 5.0 times 10 to the 4. This is the adjustment that is required if to get back into, after multiplying, you see if the result has only one digit to the left. If it doesn't, then you have to adjust the exponent so that you have only one digit to the left of the decimal point. When you're dividing numbers, you can, for example, you've got 7.5 times 10 to the 6 divided by 3 times 10 to the 2. So 7.5 divided by 3, that is the left side. And for the exponents, you minus the exponents. So 10 to the 6 multiplied by 10 to the 2 is 10 to the 6 minus the negative 2. When you minus a negative number, you are actually adding it. So it becomes 10 to the 6 minus negative 2 is 10 to the 8th. So, and 7.5 divided by 3 becomes 2.5. Similarly, if you have to adjust the decimal point, for example, if we were dividing 75 by 3, we would end up with a 25. So we would have to adjust this to 10 to the 9. And then it will become 2.5 times 10 to the 9 if this was a 75 instead of a 7.5. Now we'll talk about uncertainty. Uncertainty is when we are doing a measurement, we are not sure of all of the digits. For example, we have a measurement of 14.62 milliliters, and the instrument tells us that the precision is plus minus 0.01 milliliters. What this tells us is that when we get a measurement of 14.62, we can be sure of the 14 and the 6, but the last digit can be plus minus 0.01, so it can be either 2 plus 1 or 2 minus 1, so it will be 14. The actual measurement, status of the measurement could actually range from 14.61 all the way to 6.3. So that's what this means. So that means that 1, 4, and 6 we are sure of, so they're called significant figures. And the 2 we are not 100% sure of, so that's not called a significant figure. So in this kind of a precision, we have 1, 4, 6 as 3 significant figures, and the 2 is not, since we're not sure of it, it's not considered a significant number. Now, when we write a measurement, we have to specify how sure we are of each number. So the way it is written is, for example, if we are writing 300.16, what we are saying is we are sure of all of these numbers. Similarly, when we write 1.0200, yes, we have unlimited number of zeros after the digit, but these 2 zeros means that these 2 we are sure of, therefore they're significant. So these all 3 numbers contain 5 significant numbers, 5 significant digits. For example, 1000.0 means we are sure of the 0. So it is going to be 5 significant digits, even though it is on the right hand side. So the numbers that are always considered significant are all non-zero digits. That means anything that's not a 0, like a 3, a 1, a 6, 1, 2, 1, all of these are considered significant digits. Zeros between non-zero digits, for example, these 2 zeros are coming between non-zero numbers, they're definitely significant. This 0 is coming between a 1 and a 2, this is significant. All of the zeros written to the right of the last non-zero number are also considered significant. For example, this one has a decimal point, but after the 1, there are 4 specific zeros written over there, so they are all considered significant. Here you've got 2 zeros on the right of the 2, so they are considered significant. Here you don't see, after the 1, 6, you don't have any zeros after this, so they are not significant. Numbers that are never considered significant, the examples are zeros written to the left side of the leftmost non-zero digit. For example, in this number, the leftmost non-zero digit is a 4. So any number of zeros written to the left side of that, they are not considered significant. In this number, you have this non-zero digit here, and you've got these 6 zeros written to the left side of it, so they are all never going to be considered significant. But the zeros on the right side, as we have mentioned before, they are considered significant. So this number and this number both have different number of digits, but they only have 3 significant figures. 100 here and 416 here. The 4, 1 and 6 and 100 are the 3 significant figures. Okay, when you have zeros after the rightmost non-zero digit, they may or may not be significant. For example, the number 100, you're not sure of these 2 zeros. It could mean 1 significant figure, or 2 significant figures, or 3 significant figures. All of them will be written as 100. To solve this ambiguity, the numbers are expressed in a scientific notation, such as if you're trying to say 100 where only the 1 is significant, so you will write it as 1 times 10 to the 2. If 1 and the 0 are both significant, but the this third digit is not significant, so you would write it as 1.0 times 10 to the 2. If all 3 of these digits are significant, you would write it as 1.00 times 10 to the 2. Similarly, when we had this number, for example, here, we had 1000 with a 0 here, so you would write it as 1 times 10 to the 5, but you would write it as 1.0000. You would have 1 with a decimal followed by 4 zeros times 10 to the 4. No, times 10 to the 3. So that is how you would write. See, in here you've got 5 significant digits. So this will be written as 1.0000 times 10 to the 3. Now, some numbers are exact. That means they are infinitely precise. For example, you've got 12 inches and 1 feet. That's 100% exact. There is no 12.1 or 12.0.09 inches in a feet. It's exactly 12 inches in 1 feet. Similarly, 1 liter is 1000 milliliters, so it's exactly 1000. And the number of significant digits is infinite. 1 hour has got 3600 seconds, or in the example, you've got 42 students enrolled inside the class. 42 is an exact number. You can have a decimal point here, but it will be followed by an infinite number of zeros. That is what it means by infinitely precise. Now, when you're doing multiplication and division of different types of numbers with different numbers of significant digits. So, for example, you've got 0.92 atmospheres multiplied by 23.482 liters. You get a number like this, 0.864826127. Now, you started off with 3 significant figures here and 5 significant figures here, and you ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So, which ones are significant and which ones are not? So, the method is when you're multiplying and dividing, you take the least number of significant figures that you started off with, and that will be the number of significant figures you can take. For example, 864, these 3 can be significant because the least number of significant figures were 3 here and 5 here. So the least is 3, so you can be sure of 864. But to round it off, what you do is, since you're going to be taking only 3 digits, you round it because this is 4, 8, and 8 is closer to 50. So you round it off as 0.865 instead of just chopping off and truncating and making it 864. Similarly, if we have 4 digits here and we have 5 digits here, you will round it off as the result between this multiplied by this. You're going to round it off to 4 significant figures. Now, when you're adding and subtracting different numbers with different numbers of significant figures, here's how it's done. We've got a number like 25.6854 with a precision of 10,000th of a gram, which is 0.0001 grams. So this is a very precise measurement. But you're adding it to 0.17 grams with a precision of only 0.01. So this number is not very precise. So it doesn't really matter how many of these you had precisely, but you've got a huge amount of error range here, and you're not sure of any of these digits after the 7. So, and even the 7 you're not sure of, it could be 8 or 1. So here you've got a very imprecise number here. So you're adding a very precise number to an imprecise number. So what you'll have to do is take the least number of decimal places that were precisely known. So for example, when we add 25.6854 to 0.17, we get 25.8554. Now, since you add all of these, you end up with 25.8554 plus minus 0.1 g, but it's actually going to be 0.01 grams, which is the plus minus range because of this imprecision. And to round it off to the last two digits, you have to make it 86 because of the 5 here. So you end up at 25.86 grams with a precision of 0.01 grams, because this is the least precise measurement that you had, of which you were adding all the numbers together. Now we'll do an exercise. We have this number with 24 digits in it. The green colored digits are significant, and the objective is to convert this into a standard notation. You can pause the video here, and then you can see the result after you've done it on paper. So I will leave this slide on, and once you have done it on paper and converted this number to its standard form with these significant numbers, you can continue and then see the result. So this is the result of the exercise. You've got 6.022140076, and since you had to move this 23 decimal places to the left, see the decimal point was here, and you had to move it 23 times to get it between the 6 and the 0 to get this number. And so because of that, you have 6.022140076 times 10 to the 23. This number is also a spatial number. It's called Avogadro's number, and that's the number of items inside a mole, and this is used in physics and chemistry. I hope you like this topic of uncertainty, scientific notation, and significant figures.